Hello, Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we have seen last time the electronic spectrum of transition metal complexes. And today we will see the next point, charge transfer transitions. That is, charge transfer transitions. So we have seen the DD transitions so far in detail, and in that case we have seen that the DD transitions are taking place when the d orbital of metal shows excitation of electron from its ground state to the excited state, and during this transition the electron density is not showing any more change. The electron density remains constant. In addition to this, the DD transitions, there are other types of transitions, but because of that transitions, the charge density does not remain constant. As we have seen that in case of a DD transition, the charge density in the ground state and in the excited state remains unchanged. So there is no considerable change during DD transition. But in case of these transitions, which are called charge transfer transitions, the electron density is shifting from one location of the molecule to the other location. For example, metal ion is particularly shown at the center of the molecule, and ligands are shown around the metal ion. So if electrons are moving from metal to ligand or vice versa, these electrons are showing the charge transfer spectra, and in this case the electron density moves either from metal to ligand or from ligand to metal, and that is why such transitions are called charge transfer transitions. There are so many types of these charge transfer transitions. So during this charge transfer transitions, either the electrons are moving from the orbital of metal ion to the orbital of ligand, and this is also called charge transfer transition. Or in other way, the electrons are also moving from orbitals which are present on ligand to the orbitals which are present on the metal ion. So if the above type of transitions are taking place, if these metal transitions, metal to ligand type of transitions are taking place, then metal has filled d orbitals, and ligand has vacant p or d orbitals or s orbitals also. Then if the transitions are taking in other way, that is the ligand to metal, the ligand has vacant filled pi non-bonding orbitals, and these are showing migration of electron from the vacant orbitals of metal ion, which are either pi star or sigma star, which are either pi star or sigma star. So we can have such examples of different types of transitions. Now, if we see the specifications about these transitions, you will find that the Ligand to metal charge transfer transitions are dominant or strong, or they are used for better understanding of the concept or the process. Then, as a result of this charge transfer transitions, we find that the amount of energy required for such type of transition is comparatively high, whereas the transitions which are DD type of, the DD transitions require low energy. So they are shown in the visible region. So they are shown in the visible region of spectrum. Whereas these transitions are high energy. Because of this, they give broader bands, intense, broad, absorption bands, and they are located at blue end of visible spectrum. Blue end of the visible spectrum, and these are appearing in the clearly visible spectrum. If we observe the charge transfer transitions, these are mostly observed in the UV region or between the visible and UV region of the spectrum, but which are high in energy. So the charge transfer bands are very strong and broad. It includes also number of other charge transfer bands or absorption bands. Their extinction coefficients are ranging. Between 10 raised to 3 to 10 raised to 4 or more, 10 raised to 3 to 10 raised to 4 or more. And many such transitions are also forbidden because these are weaker. But most of the transitions are found to be observed. Most of the transitions are observed, but few transitions remain forbidden because these are weaker, and these are mainly covered by the intense and broad bands of charge transfer transitions. So, if we observe this diagrammatically, we find that the metal ions of, say, if we consider the ligands of octahedral thread, say we generally represent it as Ml6, and we generally represent it. And if this is the energy axis, and if we show these metal ions orbitals, molecular orbitals of metal ion, on this side if we show the molecular orbitals of ligand, and in between this if we show the molecular orbitals of complex. Then we can show these orbitals like this. So if we find that there are these d orbitals, so these are d orbitals of metal ion, and we can have the orbitals of ligands. So these are also having two types, sigma and pi type of molecular orbitals. So if we present these orbitals as like this, so these are, say, the sigma ligand sigma orbitals. So we will show this in simple form like this. Then the ligand also has its pi orbitals. Ligand pi orbitals. Now we will have the orbitals of ligand are lying lower energy, means during linear combination between the orbitals of metal ion and ligands. The bonding molecular orbitals are mostly that of ligands, and antibody orbitals, molecular orbitals are producible, which are mainly the natal orbitals. So these ligand orbitals are converted into these sigma orbitals. These are sigma orbitals, and these pi orbitals are also converted into this way. So we can show that these are pi orbitals. Metal ions are converted into the pi star orbitals, which are mainly having T2G, and these are also producing the sigma star orbitals, which are of Eg nature. And now, if we want to show the distribution, or if we try to show the electronic these charge transfer transitions, we show that we found that the excitation of the electrons. So these are the electrons are present here, and these are excited to this pi star. So this is called V1. Similarly, these pi star orbitals are also excited to the sigma star, and that is called sigma star transition, means second V2 transition. So that is called V2. Another way, the sigma star molecular orbitals are excited to this pi star, and these are called V3. And these sigma orbital electrons are also excited to sigma star, and these are called the V4 charge transfer transitions. So in case of this MX type of, means MX or ML6 type of complex, we observe the ligand to metal charge transfer transitions, because the ligand orbitals are filled, and these orbitals are vacant. So electron transitions means the filled electrons or electrons present in the pi orbitals are excited to this pi star, which are mainly composed of the T2G orbitals, which are of pi nature, and these are empty, there is no electron. These orbitals, electrons of these orbitals are also excited to sigma star orbitals, which are mainly contained in EG or S type of orbitals, S, 5s, 6s, etc. Then third V3 type of transition is arising from these filled sigma orbitals, which are mainly of ligand, are excited to this pi star. So the transition is sigma to pi star. So there are V1 is composed of these metal, these ligand pi orbitals to metal pi star orbitals. Then V2 type of transition is composed of these ligand pi orbitals to metal sigma star orbitals. Then V3 type of transition is composed of these ligand sigma orbital to the metal pi star orbital, pi star. And V4 type of transition is taking place from ligand sigma orbital to the metal sigma star orbital. So these transitions we have shown for easier understanding here. Now, if we see the ligand to metal type of transitions, ligand to metal type of transitions, then we find that these transitions are more easy to understand, or they are more important for understanding the ligand to metal charge transfer. So we will see how are these transitions taking place. So this is the first type of ligand to metal charge transfer transition. Ligand to metal charge transfer transitions. So they are in case of hexagonal complexes. We can have the examples of these MLX type, ML or MX, we can see X or halogens, MLX6, MLX6 type of metal complexes. So these are containing 4 types of transitions. Actually, each of these transitions is containing a large group of transitions. Since the excited orbital configuration in many cases, the ground state configuration, it gives rise to the several different stages of similar but not identical energies. Means that other types of transitions are of the same type but of not similar energy or identical energy. Now we will see what is this V1 type of transition. Now we will see this V1 type of transition. So if we see the pi orbitals are of these transitions, as we have seen here, the V1 transition, it is composed of the orbitals which are mainly present on ligands. These are orbitals mainly directed on ligands, and these are containing electrons. So the orbitals are low lying or low energy. So these are, we have shown this axis. This is lowest energy, this is relatively higher energy. So energy increases in this direction. So the pi orbitals are non-bonding and they will not vary the metal ligand distance. So these pi orbitals are non-bonding, means these are mainly of T2G type, or they can show the no change in the metal ligand distance. So this type of V1 type of transition does not show any change between metal and ligand. So there is no change. So the distance will not vary. No change. The distance will not vary much because these are non-bonding transitions. So the electrons which are present in these are not involved in actually bonding. So it shows no effect on the metal ligand bond distance. These absorption bands arising due to the charge of the transitions are narrow. These are narrow compared to other bands which are strong or broad bands. They will be missing whenever such given type of transitions are showing the absorption bands which are narrow. They may be missing if these orbitals are having if these orbitals are having the partially filled orbitals. These orbitals are having some incomplete orbitals or partially filled orbitals. So pi star T2 orbitals are filled. So when these orbitals are filled, the excitation will not take place easily to these pi star T2. So these bands will be weaker or these bands will not appear. So we will see later on in the table in which case such bands are missing. V1 type of bands are missing in case of complexes of Ru, that is ruthenium, or we can have the platinum complexes which are 5D6 configuration. So we will see it later on when the observations made from experiments are shown there in the table. So it is shown in the this following table. So it shows also that the complexes have been assigned to the V1 class of such transitions. Two trends are observed in case of such type of transitions which are taking place from ligand to mate. Two trends. What are these two trends? For example, if we take the osmium metal ion with 4+ oxidation state, their energy in the halo complexes, hexahalo complexes of MCl6, the energies are of these complexes in the following order: Ml6, then Mbr6, then Mi6. So energy required for the charge transfer transition in case of this osmium hexachloro, this hexachloro-osmium complex will be higher than that in the case of NBr6, and this is lower than this NBr6. So in this way, this order that depends upon the ionization potential of the metals, ionization potentials, and the easier oxidizability of halogen atoms. So the Cl6 is less easily oxidizable than Br-, and Br- is less easily oxidizable than I-. So the ionization potential as well as the easier oxidizability of halogen shows the energy in this order of the transitions which are ligand to metal of V1 class. We are considering this V1 class or V1 type transitions. Then as another trend observed in case of this octahedral complexes is regarding the oxidation state. This is regarding the energy. And regarding the oxidation state, we will show that the oxidation state of metal ion increases in case of say RuCl6 RuCl6 3 minus and RuCl6 3 minus, and another is RuCl6 2 minus. So here oxidation state is changing. So here the oxidation state of ruthenium is 3 plus and here it is 4 plus. 4 plus. So its orbitals should show deeply situated in the complex, and thus the transition should go to lower energy side. Now if we show the table, it will help us to understand what is the order of their V1, V2, V3 or V4 type of transitions. We will show here the ligand to metal transition, charge transfer transitions. Then we will see here the complex example, complex. Then we will show here the absorption bands, the charge transfer, absorption bands. So it will have this V1 category, V2 and V4 types. So here we are showing these molar extinction coefficients in parentheses. So we show it here actually. So first of all, we will take the example of metal having 4D4 configuration. For example, the RuCl4 or Cl6 2 minus, where here the metal ion is in the +4 oxidation state, and we will have the absorption bands in per centimeter into 10⁻³ in these hexahedral complexes. So first of all, we will show this for V1 type of conditions. The values are 17.0 to 24.5, and in bracket we will show in parenthesis 0.65 to 3.0. So here we will show that. So these values are, for example, are having the A number, that is molar extinction coefficients. So these are A and these are B values. So here we will show A indicates molar extinction coefficient values into 10⁻³ terms, and B indicates the bandwidth ranging between 400 to 1000. per centimeter. So we will show in this way the values for every type. So in case of V2, we will have the values 36.0 to 41.0, and the bandwidth values, the extinction coefficient values are here shown in this way. So here A values are in molar extinction coefficients, which are shown in parentheses. So these are 43.6, 12 to 18, any such value. Now in case of another complex V 4D5 type of complex, that is Ru Cl6 3-. Here the ruthenium is in the 3+ oxidation state. So we will have the values like this: 25.5 to 32.5 and 0.60 to 2.1. So you have to similarly refer to these values. Then here V2 will have the values 43.0 and 16, and no V4 value. Then another case 5D4. Here the example is about osmium hexachloride, that is Cl6 2-. The V1 values are 24.0 to 30.0, and these are 1.0 to 8.0. Then for V2, the values are 47.0 and 20, and there is no value for V4. Then another case of this osmium is having Br 2-. This osmium is shown here in the same oxidation state. So we are having the V1 values like this: 17.0 to 25.0 and 1.6 to 7.5. And for this V2, the values are 35.0 to 41.0 and 10.10 to 15. Then for this third example of osmium I6 2-, we have the values 11.5 to 18.5 and 2.5 to 6.0. We are having here the values 27.0 to 35.5 and 8.0 to 9.2. Then here we are having the V4 value, that is 44.6 and 41 for V4 case. Then the last examples of this is 5D6. So we are having two examples of platinum PT Br6 2- and PT I6 2-. So here PT platinum is in the same oxidation state, but the ligands are changed, ligands are varying. So in such case, the V1 values are not shown means the bands are missing. Here in this case V4 bands are missing here. So if we go to the V2 band, the V2 band is observed here. The value is 27.0 to 33.2 and 7.0 to 1.8, 18 to 18, and another value for PT I6 is 20.0 to 30.0 and 8.0 to 13. Then here we will have V4 values for this type of complex. These are 44.2 and 70 and 42, 60 and 42, 43.2, 43.5 and there it is 42, 16. Now you will find that if we compare this table with the diagram which I have shown earlier, where V1, V2, V3, V4 type of transitions are shown. So here in these two cases, the V1 excitation or type of charge transfer transitions are missing. These are not found because the pi star orbitals are partially filled or having some electrons. That is why these transitions are missing. But the next transition to V2 means sigma star are available because here sigma star orbital is empty. So that electrons are moving from pi star to this sigma star. Similarly, here the sigma star, sigma orbitals of ligand to the sigma orbitals of metal ions. That is V4 type of transition is shown here. But if you will find that in these cases, that is up to this osmium bromide, that is OSBr62-, the V4 transitions are missing here. Because these are not, means these are very low energy transitions. So we will see the transitions of V2 type. Now we will see the transitions of V2 type. So these should give the lowest energy charge transfer bands in T2G complexes. In case of platinum complexes, we find that the lowest energy, these T2G transitions are lowest energy, and the complexes are showing only these V2 and V4 bands. These transitions from mainly non-bonding level to a distinctly anti-bonding level. Non-bonding means ligand pi orbitals are non-bonding and the metal pi metal sigma star orbitals are empty. So pi star to metal sigma star orbitals are observed here in case of this. So these are fairly broad bands. The transitions assigned to V2 sets have half widths which are shown here, half band width which are shown in the brackets or parentheses. So these values are ranging between 2000 to 4000 per centimeter. So these half band widths are ranging between 4000 to 2000 to 4000, 2000 to 4000 per centimeters. The shifts in energy of these bands with the change of halogen and change in metal oxidation state are again expected from ligand to metal transitions. So you will find that the values are showing some shift between these transitions, that is V2 type. So if we take the V2 type of transitions. So here the metal ions are in different oxidation states. Here ruthenium is in +4 and here ruthenium is in 3+. So the shifting of the energy you will be observed here. So the values of absorption, molar extinction coefficients are 36 to 41, but here it is increased to 43. It is increased to 43. The bandwidths are shown here, and these values are also ranging different, but the absorption bands are shown change. Similarly here you will find that in these cases here platinum is in same oxidation state. Then transitions of V3 types are all expected to be broad and weak, and these are not observed. So we have not shown here because these are not observed. V3 type of transitions are missing. These are weaker transitions and broad transitions, but weaker transitions. They are not, the absorption bands are not rising to higher level because their molar extinction coefficients are very low values. So this is ligand to metal type of transitions. If we see the transitions in case of other examples, that is ligand to metal type of transition in say tetrahedral complex, you will find that in case of NiX, in case of nickel X4, NiX4 2 minus and COX4 2 minus and MnX4 2 minus. So you will observe these spaces will show the charge transfer transitions which are observed and assigned in much the same way as in the octahedral complexes. The charge transfer spectra are not restricted like DD transitions to the transition metal complexes. The series of complexes such as HgCl2, HgCl4, HgCl4 2 minus, then HgBr4 2 minus and HgI4 2 minus have absorption bands. So they are having absorption bands. So they will have absorption bands in this way. HgCl6-Cl4 2 minus, HgBr4 2 minus and HgI4 2 minus. So they will show you the absorption bands at 43,700 per centimeter. This will show the absorption band at 40,000 per centimeter and the 31,000 per centimeter. So if the absorption bands are occurring below 28,000 per centimeter, they will not be shown as the charge transfer bands because of their very low energy. The assigned values from ligand to metal charge transfer transitions are shown in several cases. We can see some more examples of this type of transitions. For example, if we take CDS, this is yellow color, yellow charge transfer, yellow color. It will have ligand p pi orbital transition to metal 5s transitions, and this will have the color. We have shown the colors here. Then HGS, the color is vermilion, and the transition is ligand p pi to metal 6s, metal 6s. Then another complex is Pb3 SbO4 twice. It is Naples yellow, color, and it will show the transition from ligand p pi to metal 5s or 5p, 5s or 5p. Then PbO is Mexicote color, and it will have the transitions ligand p pi to metal 6s Then we will have other examples. Pb CrO4, Pb so we are having Pb CrO4, it has chrome yellow color, and it will show the transitions ligand p pi to metal 3D. Similarly, we can have the MnO4 type of transitions. So these are some examples which are showing the specific colors. So these are V2 types of transitions. So we have shown all these for V2 type transitions. Top tetrahedral complex, that is in general we will show the molecular orbital diagram, MO diagram, for this MX4 complexes or ML4 complexes. So which are tetrahedral, that is tetrahedral. Now the diagram is like this. So we are having the metal orbitals in this direction, ligand orbitals in this direction, and Ml4 molecular orbitals in this direction. So we are showing the d orbitals in this way, and the n plus 1d. So these are nd orbitals. So we will show these nd. These are n plus 1d, 1 s orbitals. N plus 1s orbitals. On this side, we are showing here the orbitals which are having this A1 symmetry and T2G symmetry. So these are sigma type molecular orbitals. Then there are pi orbitals, T1 with T1 and T2 type symmetries. Now, the linear combination between these orbitals will show that the A1 molecular orbitals are formed from linear combination of these s orbitals and these a orbitals. So these are A1 symmetry orbitals. Now, the d orbitals having T2G type symmetry are undergoing linear combination with this T2 type of symmetry here and these T2 type of molecular orbitals. Then these T1, T2 have no comparable symmetry metal orbitals, so they are directly transferred to the MO system like this. So these are non-bonding T2G orbitals. T2 orbitals are non-bonding. So these are pi nature, and the nd orbitals are having some Eg orbitals like this. Then they are having T2G symmetry orbitals. They are having T2G non-bonding orbitals. Then the nd orbitals will have Eg symmetry orbitals, and its s symmetry orbitals. These are T2G antibonding orbitals. Then the A symmetry orbitals antibonding A1G star orbitals. So we have these A1 and these A star undergoing combination. Like this. Then this T2G. Like this. So these are the molecular or molecular diagrams. So we show the transitions from this these are T1 symmetry or whitings. So they will show the transitions from T2 to this T1. This is T1. Then T1 to EG, T1 to EG, then T1 to T2G, and this T2G to non-bonding T2G. So such type of transitions are also observed in case of various tetrahedral complexes. So you will have these observations here. So we will show these examples. So if we are the transitions for ligand T1 to metal EG, metal transitions. This is taking place at 17. So first of all we will show the types of transitions. Then second is ligand T1 to metal T2. Then ligand T2 to metal E. Then ligand T2 to metal T2 star, T2G star. That is antibonding. Now if we see the values for these observations, the values of absorption bands due to this are, we show here, is 17,700 per centimeter. And for second type of charge transport band, the values are 29,500 per centimeter. And for third type of transition, the values are 30,300 per centimeter. For fourth type of band, the values are 44,400 per centimeter. So here, the visible region, we know that visible region is marked between 14,000 to 28,000 per centimeter. So only here, so here you will find that only the T1 to E type of transition gives. So if we see this example specifically for MnO4 minus, so you will find that this transition is occurring specifically for the T1 type, that is T1 to E type of transitions. So that is, this type of transition is occurring in visible region, and that is, it gives the color deep purple. It gives deep purple color, MnO4 minus gives deep purple color. So if the question is asked like this, why MnO4 minus gives deep purple color, we have to explain in this way that this complex gives the tetrahedral complex. This is tetrahedral complex, and it gives charge transfer transitions of these four types, out of which the first type of transition is falling in the visible region of spectrum, whereas other regions, absorption bands are appearing in the high energy region. So these three bands are present in the high region, not showing the color, but it is showing only the color. And we know that the visible region is lying between 14,000 to 28,000. But these three, this absorption band is appearing about 28,000. So this is not showing any color. So with this, we will stop our discussion as a part 1 of this charge transfer transitions. In next lecture, we will see the other types of transitions. So we have seen here only the ligand to metal type of transitions. Next time we will go to see the metal to ligand type of charge transfer transitions. So we will stop our discussion here. Please subscribe to this channel and press the like button, and please see you next time. Thank you very much for watching this.